Okay, we're going to have a look at hybridisation from an IB perspective. This is S2.2.16, and the idea is to look at the hybridisation as the concept of mixing atomic orbitals to form new hybrid orbitals for bonding. Let's have a quick look at sp3 first of all. So carbon sp3 hybridisation. Carbon, you'll probably remember, has 6 electrons. Check on the periodic table if you're not sure. And in terms of the orbitals that need to be filled up, it looks like this. First 2 electrons go in 1s, next 2 electrons go in the 2s, and then we've only got 2 electrons remaining. There they are. The problem with that model for carbon, which is carbon when it's not sp3 hybridized, that model doesn't explain the fact that carbon has 4 bonds and 4 identical bonds. What we've got here is these red electrons here are spaces for example, hydrogen and methane. Hydrogen's electrons to form here and here. So this would be a covalent bond. This would be a covalent bond. Here, this looks like a dative covalent bond with both electrons coming from an external atom. The problem, of course, is that that's what methane looks like. We've got our central carbon atom here, and we've got 4 identical bonds. The bond angle between each of these bonds is 109.5. Each of the carbon-hydrogen bond lengths is 109 picometers, and the bond strength for each of those CH bonds is 429 kilojoules per mole. The idea is they are all identical. This looks like one bond between a hydrogen atom and a carbon, another bond between a hydrogen and carbon atom, and then we've got a dative covalent bond there. That does not match with what we know about methane. So, what model will explain methane? Well, this model here should explain methane. If you look, we've got our 1s orbital is doubly occupied, as in the ground state carbon. But here, with the new carbon, we've got 4 orbitals, and they are all singly occupied, which kind of matches up with how this is arranged. 4 identical covalent bonds in which hydrogen electrons can sit, forming 1 covalent bond, 2 covalent bonds, 3 covalent bonds, 4 covalent bonds, all of which are identical. The energy of these 4 orbitals, if you track it across, is less than 2p, and it is more than 2s. We give that the name sp3. Why do we call it sp3? Because what we've done is we've put one s orbital in, and another p, and another p, and another p. That's 3 p's altogether. So 1s, there's an invisible one there, and 3 p orbitals are all mixed up. And what we do is we get 4 orbitals coming out, and here they are. And the idea is that they are part character s, and 1 part character s, and 3 parts character p, which is why the energy falls in between. You'll probably realize that the energy for the sp3 is slightly closer to the p orbitals than the s orbital. This is what it actually looks like in terms of the shape of the orbitals. 2py, 2px, and 2pz are in 3 different dimensions, and they're this, it doesn't look like a dumbbell, but it's called a dumbbell shape. And that one is there. Sorry, that one is there. This one is here, and this one is here. And what we've done is we've added the 2s, which is here, and we've blended these 4 orbitals together to make sp3 orbitals. Not just the one sp3, but 2, 3, 4, 5. So this is this, this is this, this is this, and this is this. How are they arranged? Well, because they contain electrons, and remember with carbon, they are singly occupied before the hydrogen, the red electrons, have joined. Because they're full of electrons, they need to be as far apart from each other as possible, which is why they look like this. There are our 4 sp3 orbitals. 1, 2, 3, 4, and they're as far apart from each other, which here we go is reflective of the shape of carbon in methane. It's tetrahedral, and carbon that will be present in carbon whenever carbon is an alkane or in diamond as an example. So the idea is that when carbon is tetrahedral, it is sp3 hybridized. It's got this bond angle and all the bonds are identical. And the only way we can explain this setup is through this diagram here. The idea is that 1s and 3p orbitals blend together, they hybridize, they mix together. We start off with 4 orbitals, we end up with 4 orbitals that are isoenergetic, the same energy, and we call it sp3 because we've put into it 1s and 3p's. 1s and 3p's, and we've got 4 sp3 orbitals, 1, 2, 3, 4, because we started with 4. Hopefully that explains sp3 hybridization.